Hello everybody, we're going to talk about solving compound inequalities today. But before that, I want to just run through a couple of special cases, these regular inequalities and what can happen. I want to compare and contrast the difference between x plus 3 is less than x plus 3 and x plus 3 is less than or equal to x plus 3. Just like with equations, sometimes with these inequalities, strange things can happen. And we notice with these inequalities, the x, again, the variable is going to drop out. We subtract it out. We get a statement on the left, 3 is less than 3. Well, that statement is not true. That is a false statement. And for our inequality, there would be no solution. What we do on the number line is we just don't shade anything. So the number line is there, we don't shade anything. Now that's a little different from what happens on the right here. Again, we subtract out the x, the variable goes away, and we have the statement 3 is less than or equal to 3. That is a true statement, and it's going to be true no matter what. 3 is not less than, but it is equal to 3. Our answer here is all real numbers, and we want to pay attention. Just keep in mind that when we have an all real numbers, that means any number that's on that number line will solve this inequality. And what we do is we want to shade, we want to indicate that the entire number line is covered. And you'll do that differently. Some of you will be neat shader, some of you will be sloppy. I don't really care either way. So that was when the numbers were the same. We could have something like this. X plus 4 is greater than x plus 5. Again, we'd subtract out the x. We get 4 is greater than 5. That's false. That would be a no sol. And we've known each other long enough now that I will let you write no sol. Over here, if we subtract out the x, we get 4 is less than 5. That is a true statement. That would be in all reals. And we would shade above the number line or on the number line. Okay, so those special cases come up in inequalities like they did with equations. All right, so we're going to talk today about solving compound inequalities. So we've graphed them and talked about them with our idea of the amusement park. Today we're going to solve them. So what do they look like when there's x's in there, when there's variables and other numbers? We're just going to do a brief dive into these. We don't have a ton of time this year. Just as a recall, here's what we talked about with the ands and the ors. The ands, again, have different names. We call them conjunctions. We call them intersections. We call them unions. Nope, we call them intersections, sorry. Unions are the or statements. And generally, ands look like this. They're like a little segment connected. So if it was between A and B, that's an and statement. We write that as x. We can write it two ways. X is greater than or equal to A. We use the word and x is less than B. So that's saying at the same time, x will be greater than or equal to A, which would go this way forever. And at the same time, x is less than B, goes that way forever. And remember, we're looking for the overlap of those two lines, which is in between there. Better answer, we like to see it more efficiently written like this. So squished between, x is sandwiched in between our two endpoints, A and B. And again, those inequalities will always be less than or equal to's or just less than's, always facing the same direction. That's important. With an or statement, we will always see the word or in there. And we write an or statement with the word or always. There's no way to squish an or statement together. So again, if our boundary values were A and B, we would write this as x is less than or equal to A or x is greater than B. We don't need any overlap. If you're over here or if you're over here, you're part of the solution set. Okay, so ands versus ors. Today we're going to put them together. We're going to look at, they kind of look like equations. I want to deal with and statements first. These are not complicated. We just have to stop and think about what they mean. This says x plus 1 is greater or less than or equal to 5 and x plus 9 is greater than 2. So what I want to do is I want to put those two ideas together, and I'm just going to solve them separately. X plus 1 is less than or equal to 5. I could subtract 1 from both sides, and I would get x is less than or equal to 4. Well, on the number line, here's 4. We're looking at all of the values that are less than or equal to 4. That's an arrow to the left. Now I'm going to go and solve the other part of this inequality, the x plus 9 is greater than 2. And if I subtract 9 from both sides, I get x is greater than negative 7. Well, negative 7 would be way down here somewhere. All the x's greater than negative 7 would be this way. And remember, those arrows go on forever, but now what I'm looking for is where is the overlap between the two of them? Well, it's where both pieces are shaded. So from negative 7 to 4, and I'm going to put that in an inequality. Negative 7 is less than x, which is less than or equal to 4. And I tell those inequalities based on the open or the closed circle. And again, the x is in the middle, 2 endpoints, and always a less than sign. So that was pretty straightforward. We look at it, we solve each part, we think about what the answer is going to be on the number line, graph it first, and you can visually see what's happening here. But we often, actually frequently, see statements written like this instead. Now this we know is an and statement because it doesn't say the word or. If it said the word or, it would be an or statement. If it doesn't say or, it's an and statement. So how do we solve something like this? And this is the key to this lesson. This is where students make mistakes. This is like a peanut butter sandwich. Here's your bread. Here's your peanut butter. What happens when you pull apart a peanut butter sandwich? Well, that peanut butter is stuck to both pieces of the bread, and that's what we want to keep in mind here. As we solve this, we need to keep in mind that that x minus 3 belongs to both of those end points. I'm going to say 4 is less than or equal to x minus 3. And that whole x minus 3 is less than or equal to 10. So notice what I did there. I put that x minus 3 attached to the 4, and the entire x minus 3 also attached to the 10. That's important. All right, now we're going to solve them. So we would add 3, add 3. I would get 7 is less than or equal to x. And separately, add 3, add 3. I would get x is less than or equal to 13. So I pulled it apart. On the number line, here's what that looks like. This, remember I said write the variable on the left when we're about to graph it, is really this. From 7 going on forever. And then this is here, again, going on forever. What we're looking for is the overlap. So we're looking for 7 is less than or equal to x, which is less than or equal to 13. It's a weird thing to get used to. It makes sense, and we use it actually a whole lot. So we'll practice these. With an or statement, this is pretty much a straightforward deal. There's not a whole lot for us to do other than solve. We know this is an or statement because it says the word or in it. So what we're going to do is we would just take these separately and solve them and graph them. We're going to add 1, add 1. We would get 2x greater than or equal to 14 and divide by 2. X is greater than or equal to 7. So on the number line, that would be 7. Let's say 7 is here. Close circle arrow this way. Our solution set is any number that belongs to x is greater than or equal to 7 or this other piece. So I'm going to add 5 to both sides. X is less than 1, so or this. And again, that's my rule of thumb, right? And statements generally connect, or statements generally go out to the side. It's not always true. There are weird exceptions, special cases, but that's generally how we think of them, ands and or. So let's try a couple of these quickly. This is an and statement. I know it's an and statement because it doesn't say the word or. Literally, that's how easy it is. So remember what I said. We're going to pull this apart like a peanut butter sandwich. So that 2 is our bread. That 3x plus 2, that's our peanut butter. It is stuck completely to both end pieces. I know this is an and statement, so I'm going to separate this with the word and just to remind myself. That 3x plus 2 is less than or equal to 11. So as students do these, here's what we see as algebra teachers. Some kids will attach the 3x here and then the 2x here. That's not how it happens. That entire middle belongs to both pieces. All right, so if I'm going to solve, I would subtract 2. I'd get 0 less than or equal to 3x. Divide by 3. 0 divided by 3 is 0. 0 is less than or equal to x. And at the same time, subtracting 2, I would get 3x less than or equal to 9. So x less than or equal to 3. And if I were to graph those on the number line, remember this says x is, if I read it left with the variable on the left, x is greater than or equal to 0. So lightly going this way, and x is less than or equal to 3. This way, I'm looking for the overlap. What I would like to see on your final answer key is the final solution, so from 0 to 3. And I could squish that answer back together, 0 less than or equal to x, which is less than or equal to 3. And then one last or statement. Again, I know this is an or statement, literally because it says the word or. I would add 5 to both sides, 2x greater than or equal to 14. X is greater than or equal to 7. Or, now in this case, I need to remember that one big thing, that when I divide by negative 3, I reverse the direction of the inequality. X should be less than or equal to negative 9. And if I put that on my number line, here's 7, arrow to the right, and here's negative 9, arrow to the left. All right, we're going to practice some of these today and then kind of wrap up inequalities. We'll look at some special cases and plan on a quiz either middle or late next week. Bye-bye. Have a good day.